Hello, everyone, and welcome to the first video lecture of Module 1, Chapter 21. In this chapter, we will be covering heat engines and refrigerators. The concentration is going to be on heat engines. There are some few problems here and there on refrigerator, but the main concept here is the heat engine. So, what is a heat engine? An example of a heat engine is the car engine and the steam generator. For example, you have an electric power plant that works by boiling water, uh, and this boiling water produces high pressure steam, and the steam is used to spin a turbine, and then the turbine, as they spin with the electromagnetic induction, it would generate electricity. And then so in other words, the steam pressure is the one that's doing the work. And then the steam then is moved to another chamber where it condenses into liquid water, and then it is pumped back again into a boiler to boil it, and then the cycle continues again, and so on. So when we talk about a heat engine, we're talking about a system that is constantly going around in a cycle. Okay, it repeats itself over and over and over again. Okay, the car engine is the same way. You have, the cylinders. You get the air and the gasoline mixed together. They produce very, very high pressure with lots of heat. Then they push the cylinders down and up, and then the motor will start working, and that part of that heat is converted into work to move the car, and the rest of that heat is extracted to the environment through the muffler system and exhaust system, whatever. And it is, and then of course the whole system, and then more gasoline is fuel is added to the motor to repeat the cycle over and over and over again, and so on. That's the example. That's basically what a heat engine is all about. But let me show you a diagram how it works. I'll come back to this the book in a minute. Here's my OneNote. So basically, you have a diagram that looks something like that. Let me draw it here. So you have, imagine this is where the heat is coming from. I'm going to call it the hot reservoir or the heat reservoir. Okay, and then here you have the system where heat is given off to it. We're going to call it Q sub H. I'm using the notation in your book. Okay, that's heat added to the system, and H here for hot. Okay. And then as a result of that, the system does work, W, and then the rest of the heat is coming out in the form, we call it Q sub C, and it goes to the cold reservoir, okay? And that cold reservoir, we can think of it like the environment. We're going to call it CR, okay? So HR for the hot reservoir, it is at some temperature. We're going to call it T hot, for example, T sub H. And the cold reservoir, it is at lower temperature, usually much lower, T sub C. For example, for the example of the steam generator, the hot reservoir here, the temperature is 100 degrees Celsius, boiling temperature of water. And cold here, the cold water, liquid water would be, I don't know really, maybe room temperature, something like in the order of, let's say, 20 degrees or 27 degrees Celsius and so on. Okay. And so that's basically how it looks like. Now, for a perfect engine, when we talk about a perfect ideal engine, all the heat that is coming out of the hot reservoir is converted into work, which is impossible. Okay, that's basically the statement of the second law of thermodynamics. One of the version for it is that it's impossible to create a steam engine with 100% efficiency. Where, in other words, it's impossible to create an engine where all the heat coming from the hot reservoir, say the engine, the motor, is converted all of it totally into work. So here we can say that the work, trying to go to that, let's move it here. I am still new to this tablet and the stylus pen, so excuse me if my work is a little bit clumsy. So we can say that the work is equal to the difference between QH and QC. Okay? Now, this is an important equation. And efficiency, the book calls it E. I like to call it epsilon. Same thing, right? Epsilon is equal to the work divided by the amount of energy coming in to the system, which is QH. Okay? And since work is QH minus QC over QH, therefore the efficiency is equal to 1 minus QC over QH. There are two versions for calculating efficiency, either this one here or this one here, okay? Both same. Okay. Give an example and show you what that means, okay? I mean, the book goes on and on about the details of all of that. Please take the time to read it. But that's basically the gist of what we're talking about. Simple concept. So anyway, let me talk. Let me do example. Look it up. Example 21.1. Let me go to the book and read it together. There we go. I could get rid of that. There we go. Looking for the example. One more page. There we go. Is that the one? Yeah. Okay. So here, what you see here, let me says analyze the heat engine. So what you have the following cycle here to determine the net work done per cycle. So basically, okay, and B, the engine's thermal efficiency and the engine's power output. Okay, so what you're looking at is an engine that goes through the cycle from 1 to 2, 2 to 3, and then 3 to 1, and then repeats again and over and over and over, okay? So from 1 to 2, as you can see here, it is an isobaric process. And then from 2 to 3 is an isocoric process. And then from 3 to 1, this is an isothermal process, right? And each of them, if you remember from chapter 19 and 18, each of them has its own characteristic and its own flavor. Okay, so we're going to go through that. And we want to calculate Q sub H, Q sub C, and also the work. The work there, okay? It's not terribly an easy problem. It's not very hard though. Okay, so let me make a drawing of this thing. So what we have is I can't draw vertical lines with that thing. Anyway, so here is the isotherm. I'm going to try my best to make a nice looking isotherm. There we go. And then so we get something like that. And it's going from 1 to 2. This is 1 right here, 2, 3, and then 3 here is at 600, and 1 here is at 200, and then here it is at 200, and this is the pressure in kilopascal, and the volume here in centimeter cubed. Okay, and then the isotherm temperature at 300 degree Kelvin. Okay, all right. So he wants, what do you want? He said, find the work, network that is, per cycle. So we're going to take the work from 1 to 2, 2 to 3, 3 to 4, 3 here. And he wants the efficiency. And part C, he wants the power. Okay, we'll come back to that. All right. Now, one thing that is important is that the very last sentence, he said, assume the gas is monatomic. Remember when we say that gas is monatomic, what comes to my mind is this, is that C sub P, the specific heat at constant pressure, is equal to, if you remember, 5 half R, which is 20.8, whatever the units are, and then C sub V, a constant volume, is I forgot the number, 3.5. I think it is 3.5. Yes, 3.5 R, which is equal to, I have it in my note here, 12.5. Okay, whatever units are. Okay. All right. So how do we do it? So in each cycle, we want to determine the work. Okay. So let's begin by, before we do anything really, we have enough information from at point 1 here. We know the volume, we know the pressure, we can calculate the number of moles. Let's do that once and for all. So we have PV equals nRT, so P1 V1 equals nRT1, is that right? And hold on, let me make sure my video is working. Sorry about that. Yes, it is. Okay. All right, so in this case, so we have the number of moles, N, is equal to P1 V1 over R T1. P1, we're going to assume this is P1, right? Because we are in point 1 here. So that's going to be 200 times 10 to the third times V1 is 200 times 10 to the negative 6, is that right? Divided by R, which is 8.314, and times the temperature of the isotherm, 300, and then we calculate all that. And when you do that, you can end up 0.016 mole. Okay, so the N here, 0.016 mole. Okay, I lift it up. I'm using my hand on the screen to lift it. Can't think of any a different way of doing it. Okay, so let's take the cycle from 1 to 2. As you can see, here's the diagram right here. Now I'm going to use my mouse right here. So let's look at this one. From 1 to 2 here, what do we have here? This is isobaric, right? Isobaric process. And so therefore, the work, if you remember, is P delta V. So in this case, it's going to be 200 times 10 to the, what is it, negative 6? I'm sorry, 200 times 10 to the third, excuse me. Oh, I can't go there. Sorry, I have to move my mouse and pen at the same time to get this thing done. Again, because I'm ignorant. I need to learn how to use this. Anyway, so this is to the third times delta V, which basically from 600 minus 200, correct? So that's going to be 600 minus 200 times 10 to the negative 6. And when we do the calculation, I have the answer here is 80 joule. Okay, so the work from 1 to 2 is 80 joule, and it's positive. Positive because there has been an expansion. Is that right? Okay. What about the temperature? So let's say I want to know what's the temperature here at T2. I mean, the isotherm is 300 Kelvin. What is the temperature here? Well, since it's isobaric, which means the same pressure, so I can use, what is it, V1 over T1 equals V2 over T2. Therefore, T2 is equal to V2 over V1 times T1. That will be equal to, look at the diagram here, guys, to the left. So that's going to be 600 regardless of unit divided by 200, right? Times 300 Kelvin. That gives me, this is 900 Kelvin, right? There we go. I have T2 is 900 Kelvin. Come back to this, it'll become useful later. That's basically, so what I'm saying here is the temperature have increased from 300 to 900 3 times as a result of this isobaric process. Okay, there we go. So we know pretty much everything. The last thing I want to get out of that in this cycle is the Q value. this Q value is basically the Q hot. Okay, so it's so what is it? How do I calculate the Q value? Since it's monoatomic and it is isobaric, if you remember, that's equal to N C sub B delta T. Remember that? So here we have 0.016 for the number of moles is right there. Whoop, not here. Number of, oh, sorry. There it is, 0.016 times C sub P. We know it is equal to 20.8, 5 half R, 20.8 times delta T, which is 900 minus 300. That gives me 200 joule. Okay? So this is basically Q hot. In other words, the heat that enters the system. Heat enters the system. How do I know that? Well, look at the temperature. It started with 300, now it is 900. So you have heat has entered the system. That's the Q hot. Okay, this engine. So now we know everything. We know W. We know heat that enters or leaves the system. Okay. Now we move on to the next process, which is from 2 to 3. Okay, I'm going to lift it up. Now we have process from 2 to 3. So here we have isochoric, which means delta V equals 0, and that's tells me that the work is 0 as well, right? There's no work there. Okay, so here, remember, for constant volume, C sub V is equal to 3 half R, and that would be equal to 12.5, whatever the units are. Okay, and now, since we are on 3 here, right, that means we're back to the isotherm. So that means the temperature T3 is 300 Kelvin, right? So whatever heat is generated there, that heat is extracted, come out, remember? Okay? So this is heat in because the temperature have increased. There has been heat coming in. Here, when we whatever Q value that I calculate here, it's extracted. That's QC in this case, okay? It goes to the cold reservoir. Okay. So let me calculate that since we're talking about it. Lift it up a little bit. Q sub C is equal to NCV delta T. That will be 0.016 number of moles. CV is 12.5 times delta T, which is 300 minus 900. Look at this negative, but it's out. And then I'm going to give me, this is going to give me negative 120 joules of heat. So this is QC. Okay? Let me box it here. So this is heat leaves the system. All right. So the work is 0 as well, right? Did we mention that? Okay. Now we come to the cycle from 3 to 1, the last one. So this is an isothermal process. Okay. And what's so special about isothermal? Delta U is 0, delta T is 0. There's no change in temperature as well. And as a result of that, you remember from the first law of thermodynamics, is W and Q are equal. Right? Okay, so let me calculate W. And if you remember, W for isothermal is nRT natural log of V final over V initial. So that makes it V1 over V3 for our case, correct? And that's going to give you a negative answer because V1 here is smaller, right? So let me calculate that. So that's 0.016 times R, 8.314, times the temperature is 300 Kelvin, times natural log of, 2 over 6. Is that right, guys? That's 1/3. The units don't matter anymore, right? Because you take a ratio. So anyway, we calculate this, and I end up with negative 44 joule. And we say, but W is equal to Q, which is QC, that is. QC, right? And so we have here negative 44 joule heat as well. Okay, has been extracted. So, okay, I'm done with it. I'm done calculating all the cycles. I'm done calculating Q and W for all the cycles. And now I'm back to the question number A. He said question part A is what is the net work, right? So net work would be a cycle from one to two plus the cycle from 2 to 3 plus the cycle from 3 to 1, right? So from 1 to 2, we calculate to be 80 joule. From 2 to 3, that's isochoric, remember, it's 0. And then from 3 to 1, that's a negative 1, is 44. So the net here is that we have gotten a net work of that. You see what I'm saying? That's for this heat engine, with all the heat that is given to us, not given to us, the heat that we have that entered the system, remember, which is, what is it? We calculated already right here, right? This is the heat that have entered the system, 200 joule, right? And this heat has given us work, 200 joule, equal to 36 joule. That's it. You see what I'm saying? So I can calculate the efficiency. It's not much, really. But the efficiency in this case, epsilon, is work over QH, and that's equal to 36 over 200. That will be 18%. Okay? Got it, guys? Okay. Now, part C is not difficult. He says, let me read it again. He said the engine's power output, he said calculate, okay, determine the engine's power output if it runs at 600 RPM, okay? So what does that mean? Well, okay, so the RPM, that's how I like to think of it as frequency. So that's 600 rev per min. Let me convert it to hertz, always revolution per second. So it's going to be 600 divided by 60 rev per sec, which makes it, what is that, 10 hertz. Hertz is rev per second, right? So there we go. So the frequency is 10 hertz. Why do I need that? What is the power? Well, I know that power is equal to work over time. What is the time here? The time is the period, okay, the time it takes to complete one cycle, the time it takes to go, look at my mouse here to the left of the picture. The time it takes, how did that happen? Anyway, the time it takes to go from 1 to 2 to 3 to 1, and so on, okay, the time it takes it is the period. And we know that, if you remember from previous physics courses, is tau, which is, let me go back here. So that's work over tau. So tau here is 1 over F. So that'll be 0.1. Okay. So it takes it, that's a kind of a slow moving engine, I guess, 0.1 second to one cycle. So therefore, the power is work, which is, we have calculated to be 36 divided by 0.1. So the power here is 360 watt. A small engine, I guess. And there we go. Got it? Okay. Let me do another problem. Let's see. I'm looking for not too easy, something kind of a middle difficulty. I don't know. Let's do number 14. Okay. In the home, I believe it's homework. I'm not sure. I have it marked here. Let me look at the book, number 14, and let me go to this problem in the ebook. So for you to see it, how do I do this? Here and chapter 21. summary question to be there. And number 14. There we go. 14. Okay, there we go. Okay. Okay, it says figure 14. What is this? This is figure 14. Okay. So it says here, he said, so you look at this number 14 right here. Okay. It says here, we have this diagram, this cycle. Let's see, he said he wants what are the work, basically the work output. Out means output. And the how much heat it enters the system, the engine. You want to calculate that, and the thermal efficiency. Now, when you see something like this, an arrow coming out, most likely it is QC. In other words, heat extracted from the system. The Q sub C. Most likely, okay. So let's do this problem. Try to make a horizontal line. It's so hard to do. Okay. Number 14. I wish I could expand it. Can I expand this thing? I don't know if I can do that. Oh, there. No. Anyway, I'll just live with it. So he said, find A, work, and UH. Okay? And B, find the efficiency. Okay. Well, it's not that bad. Let me draw it very quickly. So what I have is I have a triangle that looks something like that. This is 100. I can't draw a vertical line. It's anyway right here. I apologize. 200. This is volume in centimeter cubed, and this is 400, and then this one. It needs there is a learning curve for writing with the stylus. I'm talking here. I'm talking directly on the tablet. I'm using a PC. The pad is on the table, and then I'm writing on the screen. There is a learning curve to it. I've been practicing for a while, but I haven't. Hopefully, I will become easy later for me. But for now, it's still a struggle. And I really miss being in a classroom with you guys. I do enjoy being in a classroom rather than online. But anyway, let's get sentimental here. All right. Okay, so he wants to get the work. We'll find the work, that is. The easiest way to do it is, let me change the color to red. The easiest way to do it is to, since we're dealing with a, kind of a nice looking geometric system, all we need is just to get the area under, not area under the curve, the area of the cycle, okay? Like this. Get the area of the triangle. This is how you get the work. We couldn't get it in the previous problem because it's an isotherm, so it's kind of complicated. But this one is basically just a triangle, half the base times the height, and you should be able to do it, right? So the work is nothing but the area of the cycle. Let me write it down here. So the work is equal to half the base times the height. That will be half the base. What's the base? The base is basically the length of the isobaric process. This one here. That will be. Am I right? Yes. So that's going to be from 200. I'm sorry, 200 minus 100. Correct? Yes. So that's going to be. I'm sorry. Hold on. Let's say that. I mean, I need to determine what is the height and what is the base. Let's assume the base is this one. Okay, that's the base and that's the height. So if this is the height, then it is 400 minus 200, correct? Times 10 to the third, the scale of Pascal, times the base, which is 200 minus 100 times 10 to the negative 6. So that'll be 1/2. I hope I did it right. Did I do it right? Does that sound right to you? So that will be 200 times 10 to the third times 100 times 10 to the negative 6. Let me calculate that. I have, that will be 200, what is this? I've gotten an answer of 10 in my notes, but I'm doing it differently. 200, 1, 200, should be the same. So time times 0.5. Yep, we got the same answer. Okay, good. So what we get is 10 joule. There we go. I think I did it right. I don't know how I did it in my notes. It looks very different. But anyway, there we go. So we got the work is equal to 10 joule. Okay. Now, he also says find QH. Well, it says in the problem that this is the heat extracted. See that? This is heat extracted. So that's basically QC. Okay, that's basically the trick. So here, given QC is negative, what is it? 114 joule. Okay, the minus means heat extracted. So we know that work is Q hot minus QC. Therefore, Q hot is W plus QC. Okay, and remember we have to when we add up those, we basically want to get the absolute value of that. Okay, so that's going to be 10 plus 114, and that'll be 124 joules. Okay, so that's how much heat has been entered the system. Heat enters system. This one, however, heat leaves the system. Okay. And the last step, he said, what is the thermal efficiency? Epsilon or E, whatever. It's basically work over QH. That will be, we calculate work to be 10 divided by 124, and that gives me 8%. Okay, so that's what it is. Okay. Okay, awesome. One more problem. I like this one, number 13. Go back to it. Oh, it's right here. Okay, there it is. Okay, so what you have this diagram right here, this one right there. Okay, let me draw it. Look more like a square, I'm not sure, but anyway, here it is. And so it's a cycle. Remember, it's a cyclical system. And this is 100, this is 200, this is 200, and this is 400. This is in kilopascal, the pressure, and then this one is volume in centimeter cubed. And so here we have heat leaves the system, which is QC, Q equal negative 90 joule. And then also heat leaves the system here in this cycle, Q equals negative 25. What that means that the total QC is you add those up together. You know what I mean? So you add them up together. That will be the total heat extracted or left that left the system. Okay. Now he's asking what is the total work, QH, and the thermal efficiency. Is that it? Yeah. Okay. Same stuff. So work, since this is a nice geometric shape, we can just get the area of the cyclical thing here. It's just the area of the cycle. Okay. You can get the area under the curve. Same thing. You can get the area of the curve from here. This under this curve. Then under this curve, we subtract them. It's the same thing, right? So it won't matter. Anyway, I want to get the area of this one. So work is the area, and I think it's going to be long. So let me just go maybe below the curve right there. So in this case, basically what? Length times height. So let's start with the length, which is this one here, horizontal length. So that's going to be 200 minus 100 10 to the negative 6 times the height, which is 400 times 10 to the third, okay, minus 200 minus 100 times 10 to the negative 6 times 100 times 10 to the third. I mean, that's one way to do it. Is you get this under this curve and then under this curve, and then you get that. There is a different way of doing it. You do it your own way. Hopefully, you get the same answer. Then you do the calculation, pretty simple calculation. You'll end up with that the work is equal to 30 joule. Okay, there it is. And it's positive work. That means overall it is doing work. Okay? All right. Now, okay. So since I have here Q, this is leaving the system. Those heats are leaving the system. That means QC. So total QC here is basically 90 plus 25, and that'll be equal to what is it? 115. Okay, so that's QC. And therefore, since work is Q hot minus QC, so Q hot is W plus QC, and that gives me 30 plus 115, excuse me. And that gives me Q hot is equal to 145. Okay. And then the last thing, he said, what is the efficiency? Efficiency is work over Q hot, and that would be equal to 30 joule over 145 joule. Their efficiency in this case will be 21%. Okay. That's it. I think this is it. This is I can do one more. Finish. Um, you know what? I think I'm going to stop here. If you have any questions or about a particular problem, you're more than welcome to, go under Ask the Professor. Let me show you what you got. Here is our course right here, and the video lecture is gonna be posted here. This is the video that I'm making. This is Ask the Professor right there. If you click on that, and then you can just post your question here about just say, Dr. Raja, what about problem number so and so? If you want me to do it, I'll be more than happy to do it, either in a video or I'll give you some hints on it. That will be one option, or you can just come down here and shoot me an email. I prefer to keep the email for personal things. Let's say you want to discuss whatever personal, you can shoot me an email. But if it's something that has to do with class and you think it's going to benefit your classmates, I prefer to use Ask the Professor forum right here. Okay, and that's it for now. Let me know what you think of this video, and if you need any maybe another video for me to do for you on this chapter. And next week, I believe this chapter only runs for 1 week because it's short. That's just my opinion. And next week, we're going to move on to a very new topic. We will be done with thermodynamics, and we will be do. What is the next week topic? I forgot. Let me look it up. By the way, the course schedule, you can just click on that, and then you'll get it as a Word file. Okay. But the next week, there'll be chapter 16, Traveling Waves, and that's kind of a long chapter. So we're going to be doing this for 2 weeks. Okay. Oh, I'm sorry. Chapter 21 is 2 weeks right there. I didn't see that. Well, that's fine. Okay, so 21 is for 2 weeks. So you still have until April 5th. So please let me know if you have any questions. Okay, and I will end the video right now. And have a wonderful week. Bye bye.